Hi, my name is William Johnson, and I will be presenting the Physics 2211 Lab 2, Motion of a Falling Object. In this lab, I will be going over the key concepts to introduce the lab, analyzing the crumpled paper's motion via tracker, creating two computational models based on Newton's second law, one dealing with only gravitational force, and one dealing with both gravitational force and drag force. I will then do a model comparison and answer the questions what if and what does it mean. The purpose of this lab is to analyze the motion of a piece of crumpled paper as it accelerates after being dropped from rest. I will then design two computational models via GlowScript to replicate a real-world scenario of an object being dropped, one with just gravitational force acting upon it, and one with both gravitational force and drag force acting upon it. I will then compare the observational model to both the computational models and identify any key differences. A quick summary of the results of this lab are that the computational model that implemented both drag force and gravitational force was more accurate to the observed model than the model which only included gravitational force. A couple key concepts of this lab are that this lab explores Newton's second law with a net force not equal to zero. Newton's second law states that the acceleration of an object is dependent upon two variables, the net force and the mass of the object. This can be represented by the net force is equal to the change in momentum divided by the change in time, which can be rewritten as final velocity is equal to initial velocity plus net force divided by m times the change in time. That velocity update formula is related to the position update formula by the final position is equal to the initial position plus the average velocity times the change in time. This lab also explores the concept of gravitational force. The gravitational force near the Earth's surface is gravitational force is equal to negative mg times j hat. In this equation, m represents the mass of the system the force is acting on, g represents the acceleration of the object due to gravity, and j hat represents the direction the force is acting. Acceleration due to gravity is approximately 9.8 meters per second squared. In one computational model and the observed model, drag force is also present. Drag force can be best represented by this equation. Drag force is equal to negative b times v squared times j hat, with b representing the proportionality constant, v representing the velocity the system is moving at, and j hat representing the vector that points in the direction of the force. Here's the video to analyze the paper's motion. As you can see, the crumpled paper falls downward with an increasing speed due to gravitational force. The mass of this paper is 0.02 kilograms. The initial position vector is 0, negative 0.01052606. The initial velocity vector is 0, negative 2.126360. Here's the code for the first computational model that only includes a gravitational force. Ball.m is set equal to the mass of the crumpled paper. Ball.pos is set equal to the initial position of the crumpled paper. Ball.vel is set equal to the initial velocity of the crumpled paper. G is set equal to the acceleration due to gravity. In the while loop, t is less than 0.29, so the last timestamp that we wanted was 0.300. The variable w is set equal to the gravitational force equation, and the F net is set equal to the equation of the net force acting on this piece of paper. Ball.vel in the while loop is set equal to the velocity update formula, and ball.pos is set equal to the position update formula in this while loop. Here's the code for the computational model that dealt with both gravitational force and drag force. The code for this model is the same as the previous model, except drag force is included. This is shown by the variable b, which I calculated to be 0.0087. Also, the drag force in this equation was entered into the while loop. Here's the model comparison. The computational model that included both drag force and gravitational force was far more accurate to the observed model than the computational model that only included gravitational force. The model without drag had a steeper slope and became less accurate as time went on. This is because drag is not accounted for, which means that the ball is predicted to fall at a faster rate due to no counterforce to gravitational force. Now I answer the what if and what does it mean questions. The computational model that includes drag and observational model both predict a terminal velocity will occur in the future. In both of these charts, it can be slightly noticed that the slope is becoming closer to a constant value near the final time, signifying a terminal velocity. This is because the force of drag pointing up is becoming closer to being balanced with the force of gravity pointing down because the velocity is increasing, causing the force of drag to increase. Even if the crumpled paper was thrown downward, it would have no effect on the terminal velocity. Although the crumpled paper thrown down and the crumpled paper simply dropped might reach a terminal velocity at a different time, the terminal velocity would not change. In summary, this experiment highlighted the significance of Newton's second law, gravitational force, and the influence of drag force on free-falling objects.